Well, welcome back. We've got some really good application to talk about today. We'll start out. I want to introduce you to what a laser is, okay? And then we're going to have a separate, the whole separate video on just playing with lasers. So I want to introduce you to this, and then later on in this unit, we'll show you. We'll have you watch a video on lasers themselves. So once again, the word laser is actually an acronym where the first letter stands for something and the whole deal. So the L in laser stands for light. Now, we'll talk about this in our regular laser video, but a regular white light just goes and diffuses out, okay? But then the A stands for amplified. So if you are playing a guitar and you have an amplifier, what does that amplifier do? It makes the sound louder, makes it more resounding. Okay, well, so this is going to make the light more intense. It's going to break it down even more. And then S stands for synthesis, okay, or synthesize. So if you have a synthesizer in music, you bring it all in and it hones it all in. This brings the light into one beam, one monochromatic beam. We'll talk about that when we do the whole laser video. And then E stands for emissions. Emissions means to give off a beam of particles. In this case, we have alpha particles and beta. We talk about this in the laser, but we have emissions of, and R is radiation. And we'll talk about what radiation is. So we talk about a laser. It's light amplified, synthesized by emissions of radiation. So that's what laser stands for. Years ago, lasers weren't that common. Now they're really common. I will show you a lot of different kinds of lasers in the laser video. I'm looking forward to that one. I have fun in that one myself. So how does a laser work? Okay, now here's the chemical application. A laser shocks these electrons to a higher energy level. When they come down from that higher energy level, then they produce light or heat or radiation. So even the fluorescent lights that we have in this room, even the fluorescent lights are actually shocking a series of electrons. They're going from the S electron to the P, from the S orbital to the P orbital, from the P to the Ds. So once they go up an energy level, when they come down, then they give off, in this case, they give off light. Now, the efficiency of a system determines, I want light out of this, so I don't want it to give off much heat. So an efficient system for the fluorescent light is going to give off light. A laser gives off pure light. There's going to be a little bit of we'll show you some heat lasers that want to give off heat. So it's kind of cool. So a lot of applications for lasers, but the main thing is, the chemistry thing is, what we're looking at with the laser is that we are shocking electrons to a higher energy level. When they come down, we want to know if they're giving off light, heat, or radiation. So that's just a brief introduction of what the acronym laser stands for and how it works, but we'll have a whole video on lasers that will be part of the chemistry application part of this class. Now, we're going to learn a couple different skills here that are critical for chemistry. First of all, we're going to call this, there's two different names. There's kind of an old school and a new school, so you may see both. Gram molecular mass, okay, abbreviated GMM, and then gram atomic mass, GAM. Now, once again, we kind of got old school, we kind of have new school, so you may see both of these, but I just want you to know that's the same thing. So whether you're talking about GMM, gram molecular mass, or GAM, gram atomic mass, it's the same difference. Now, here's what we want to do. It's really simple. I put some examples here. We're going to use our periodic table. Now, what we're really going to do here is we're going to look at the atomic mass numbers, and we're just simply going to add them up, okay? So we talked about this earlier. So here's hydrogen. The atomic number is 1. We don't want that. We want the atomic mass number, 1.0079. Now, there are some times where we're going to be exact and we're going to use all these decimals. But what we're going to do right now is we're going to use approximation. So we're going to round these numbers off to the nearest whole number. So let's calculate the gram molecular mass for water. Okay. So once again, we look at the subscript, we see that we have 2 hydrogens. So once again, the gram molecular mass for hydrogen is 1.0079. So we're going to round that off to 1. Okay. So the hydrogen is equal to, there's one of them, the atomic mass is 1, and there's 2 different ones, so 1 times 2 is 2. Okay? So then we look at oxygen. So we come over here to oxygen. The gram molecular mass here is 15.9994, so we're going to round that up to 16. So for oxygens, okay, it's the gram molecular mass is 16, and we only have one of those, so that's 16. So the gram molecular mass is 18 GMM. Now once again, that can be GMM or that can be GAM the same way. So the gram molecular mass is simply adding up the mass numbers for each of these. So let's do carbon monoxide. So we look at carbon, 12.001, okay? So once again, what a chemist does a lot of times is takes this, and rather you can write it out like this if that works for you, okay? What we do a lot of times is we just draw an arrow here. The carbon is 12.001, so we're going to round that off to 12, okay? Oxygen, once again, 15.9994, we're going to round that off to 16. So this one would be 16, but we have two of those, so 16 times 2 would be 32. All right, so we add those together, so the gram molecular mass for carbon dioxide is going to be 34. All right, so once again, it's just a matter, and that gram molecular mass, gram atomic mass is the same thing. So once again, we're just adding the gram molecular masses together to get the total gram molecular mass for that element. So now let's do, so we might see it like this, we might see it like this, or they might say we have 3 moles of hydrofluoric acid. Remember your naming, okay? So 3 moles is the same as saying we have 3 molecules of this. So hydrogen, once again, we know is 1 because it was 1.0079. And then we look at fluorine. Fluorine is 18.998403. So when we're doing approximation, we're going to round that up to 19. So once again, so we have 20, okay? But there are 3 moles of those, so we have 3 times 20. So we have 60 for the gram molecular mass or the gram atomic mass. So as you can see, once again, it looks kind of complicated as we go. But once again, chemistry is pretty easy once you understand it. Now, then the other form that we have would be just, it simply has the molecular number, the number of moles out front, and then it has the subscripts as well. So now we want to calculate how many of each element. So carbon, once again, we look up at our periodic table. Carbon is 12, okay? And oxygen, we look at oxygen here, it's 15.99, so we round that up to 16. But we say, okay, how many carbons do we have? Well, we have 2 carbons, okay? Why? Because the mole number is 2, okay? So there's going to be 24, so the total value for the carbon is going to be 24. But how many oxygens do we have? Well, we have the mole number is 2, the subscript is 3, so we have 6 of those, okay? So that's going to be times 6. So 6 times 6 is 36, 3, so 96. So we're going to add those together, okay? So here we go. There's 10, 9, 10, 11, 12. So 120, all right, is the gram molecular mass for 2CO3. So once again, just a quick explanation here. If you're having trouble with that, go back, practice these things. If you're having any trouble with these, practice, put these down, try different ones, practice them. Go through, but once again, this is just simply the gram molecular mass number for each of the different elements that are involved. Now that leads us into percent composition. Okay. Now, no matter where you're at, percent is always part divided by whole times 100. Okay. So part divided by whole times 100. So now we can take different things. Like for example, let's take for example hydrochloric acid. Okay. Get us a little bit of a board space here. Okay. Now, we're going to do the same gram molecular mass to determine this, and that's going to determine the whole and the part. So, in percent composition, which is extremely important to chemists, we want to know what percent there are of different things. So, let's figure the percent hydrogen in hydrochloric acid. Okay, so this is a good example here. So, once again, percent is always part divided by the whole times 100. All right, we'll just put a smiley face on there. Okay, so I want to know the part. Okay, so the part is hydrogen, the whole is hydrochloric acid. So let's see what the gram molecular mass, let's see what the whole thing weighs. Well, here we go. Hydrogen is 1.0079, so we're going to round that off to 1. Okay, chlorine, we're going to come over here. Okay, now, I love using chlorine. Okay, I love using chlorine because chlorine, is the gram molecular mass is 35.453. Now, let's look at how we round that up. So we might say to ourselves, oh, that's not a 5, so we don't round that up. But actually, really, what we have is, does this 3 change that 5? No, that 3 doesn't change that 5. Does that 5 change that 4? And the answer is yes, because since that 5 is 5 or greater, then it's going to change this 4, okay? It's going to change that 4 to a 5, which is going to round this up to 36, okay? So when we do chlorine, we round that up, 35.453, it rounds up to 36. All right. So what's a gram molecular mass rounded up of chlorine? It's 36. So we add those, so it's 37. So it's kind of cool. So what does the whole thing weigh? Well, the whole thing, the gram molecular mass is 37. So I've got 37 for the whole. What do I have for the one? Oh, the part. I want to know part. Hydrogen in hydrochloric acid. Well, the part is 1. So I have 1 divided by 37 times 100. Now, once again, even in your syllabus, it talks about this. The only calculator that you really need for this class is just does basic operations. You don't need a scientific math calculator. You do need something that does exponents, but just any TI 30 or above calculator works for this. Same deal here, 1 divided by 37 times 100. And let's see what we did here. Let's see, we did, let's see. So, when we did that, we got 2.777, and decimal places, we're going to round that up, so we're going to get 2.8% hydrogen. Okay, all right, there we go. So decimal places, we want at least 1 decimal place up. We could even do 2.78. We'll talk a little bit later about significant figures for decimals. If in doubt, decimals or percentages are usually 1 or 2 decimal places. So if you want to do 2, that's great. Or if you want to do 1. So once again, the percent hydrogen, 2.8% or 2.78% hydrogen. Okay. Let's do one more for practice. Let's do sulfuric acid. Okay. Let's do sulfuric acid. So one of the questions we may ask you on your test, and I'll start this and then I'll let you finish it in your notes just to make sure that you know what you're doing. So once again, I told you on the nomenclature that you will have to know sulfuric acid, H2SO4. So the question might say, calculate the percent composition for every element in sulfuric acid. Okay. So you need to know that sulfuric acid is H2SO4. So let's go through and do the whole thing, okay? So once again, hydrogen is 1. There's 2 of them, so there's 2 for hydrogen. What is sulfur? We come up here, we find sulfur is 32.06, so that's plus 32. Now, each oxygen is 16, okay? All right, how do we get that? Because it's 15.994, so it rounds off to 16, and there's 4 of them, so 16 times 4. Okay, so 6 times 4 is 24, 2, 4, 5, 6, so it's 64, okay? So now we add all of those together, okay? So we add all those together, we get 2, 4, and 4 is 8. It's always a good idea to do this on your calculator, okay? And 30 and 60 is 90, okay? So 98 is the whole, okay? So 98 is the whole. So I'll just put these in and let you punch them into your calculator and check your math. But let's do the percent hydrogen, okay? So what's the percent hydrogen? Well, the part, it's H2, so the percent hydrogen will be 2 divided by what's the whole? 98 times 100, and that's going to equal the percent hydrogen. Well, let's think about this. What's the percent sulfur in sulfuric acid? Well, sulfur is 32, okay, and the whole is still the same, 98, so times 100 equals the percent sulfur. Now let's do oxygen, the percent oxygen in sulfuric acid. The part is 64, okay? The whole is 98, so times 100 equals the percent oxygen. So this gives us an idea, so now we can go through, we can calculate percent composition of any single compound that we have. So once again, that's a skill that you're going to need to know. Practice it, go over it, do some different ones. It's a good opportunity if you're in a study group with somebody else or you're in a dual credit class. Spend some time with other people. Do some, see if you get the same answer. If you're having problems, notify me on Moodle and we can give you some more instruction on that. But once again, gram molecular mass, we're going to add up the mass numbers of the total element, and percent composition is always part divided by whole times 100. Now, let's move on to 2 more items that we're going to have for this unit. First of all, we refer often to standard temperature